Welcome back to the deep dive. Have you ever looked at a complex molecule and just wondered, how do chemists make a reaction happen exactly where they want it to?
Yeah, especially when there might be like a dozen other possible spots.
Exactly. It feels almost like molecular surgery, you know? It must require incredible precision.
It really does. It's a challenge that, well, it defines a lot of advanced organic synthesis. We've talked before about chemoselectivity.
Right, choosing which functional group reacts.
Exactly. But today we're diving into regioselectivity. So if a functional group could react in, say, two or more different places on that group or nearby,
Right.
how do you force the reagent to pick just one specific spot?
Ah, okay. So it's all about controlling the where, whether you're adding something to an alkene or sticking a substituent on a benzene ring,
Right.
getting that location right is fundamental.
Totally fundamental.
And our mission today, really, is to unpack the fascinating ways chemists manage this control. We're going deep into the mechanisms that dictate the where, using Chapter 24 of Clayden, Greaves, and Warren's Organic Chemistry as our main guide.
Which is a fantastic resource for this stuff. Really drills down into the reaction pathways and functional group transformations.
Definitely. And you'll see how this kind of precision affects everything from making life-saving drugs to, well, creating totally new materials.
Okay, so where should we start? Maybe with a classic,
Ah,
electrophilic aromatic substitution.
good call. The benzene ring. We know from previous dives that substituents already on the ring direct incoming electrophiles,
Yeah, electron-donating groups tend to push new groups to the ortho or para positions.
while the electron-withdrawing ones send them meta.
Right. But what's interesting is, while meta-directors are often pretty selective for meta, those electron-donating groups, they usually give you a mixture of ortho and para.
Ah, so if you specifically need just the ortho product, especially if that spot is kind of crowded, sterically hindered, you got a problem.
You do. That's the classic ortho problem in synthesis.
So how do chemists get around that? How do they reliably nail that ortho substitution, even when it seems like the toughest spot to hit?
Well, this is where designing the reactivity really comes into play. A super powerful technique is called ortholithiation.
Ortholithiation, okay.
So instead of just throwing an electrophile at it, you first deprotonate the ring, usually with a really strong base, like butyllithium. But here's the key. You need a directing group already on the ring, something like a methoxy group or maybe a tertiary amine.
And how does that how does it work? Does it kind of like flag the spot?
Pretty much, yeah. The lone pairs on the oxygen or nitrogen of that group, they can sort of grab onto or complex with the Lewis acidic lithium atom from the butyllithium.
Ah,
And that temporary connection, it acts like an internal GPS. It guides that strong base to pull off a proton only from the adjacent ortho position, even if it's sterically hindered.
wow. So it forces the reaction right where you want it. Like you said, molecular surgery with a guide beam or something.
Exactly. It turns a difficult spot into the prime target. And the aerolithium you form then is super reactive, a great nucleophile for whatever you want to do next.
Any big real-world examples of this?
Oh, definitely. The synthesis of fredricamycin, it's a potent antibiotic, relies on 3 consecutive lithiation reactions. 2 of those are ortholithiations, used to build up its really complex structure. It just shows the power of this strategy.
That's incredible. 3 times. Okay, but what if you don't have a good directing group for that? Or maybe you need to block a position, but just temporarily. Is there another trick up the sleeve?
Absolutely, and this one's really neat, using reversibility, specifically sulfonation.
Sulfonation, adding an SO3H group.
Right. But unlike most electrophilic aromatic substitutions, sulfonation is unique because it's reversible if you heat it up. The sulfonic acid group can actually pop back off as SO3 gas.
Wait, hang on. You can put it on and then just take it off again. So you use it like a temporary placeholder you can erase later.
You got it. That ability to mark and then unmark a spot. It gives chemists amazing strategic control. It's like having an undo button for synthesis.
Okay, that sounds incredibly useful. How would that work in practice?
Well, think about making 2-bromophenol. If you just brominate phenol directly, you'll mostly get the parabromo stuff, or even tribromophenol, because that OH group is a strong orthopara director.
Right, it activates those positions. So how do you force it to just the 2 position, the ortho position?
You use sulfonation as a blocking group. You can sulfonate phenol, first blocking the para position, then maybe sulfonate again to block one of the ortho positions.
So you end up with phenol with 2 sulfonic acid groups attached.
Exactly. Now, 2 of the 3 most reactive spots are blocked. So if you add bromine now,
It really only has one place to go, the remaining open ortho position.
precisely. And then the clever part. You just heat the mixture up. The sulfonic acid groups pop off.
And you're left with your desired 2-bromophenol. That's brilliant.
It's a fantastic example of using kinetic versus thermodynamic control and temporary blocking groups.
That balance between sort of the fast product and the stable product, that's not just for phenols, right?
Yeah.
Doesn't it show up in bigger aromatic systems too, like naphthalene?
Oh, absolutely. Naphthalene's interesting. It has two different types of positions, alpha and beta.
Right, near the corner versus along the side of the two fused rings.
Yeah. And electrophilic attack usually prefers the alpha position. That's generally the kinetic product, because the intermediate cation formed there is better stabilized. The positive charge can spread out more easily.
So bromination, for instance, mostly goes alpha.
Mostly alpha, yeah. But if the reaction is reversible, like sulfonation, and you heat it up.
Let me guess. It rearranges.
Exactly. That kinetic alpha product can revert, and eventually you end up favoring the more stable thermodynamic product, which is the beta substituted one.
Why is beta more stable thermodynamically?
Usually less steric hindrance, especially with a bulky group like sulfonic acid. So just by changing the temperature, you can flip the regioselectivity completely from alpha to beta. It really highlights how conditions dictate outcomes.
Man, that just drives home how much planning has to go into synthesis. You can't just mix things together and hope. It's all about strategy.
It absolutely is. Choosing the right sequence of steps is crucial. Take the bromonitrobenzene isomers. You want ortho, meta, or para.
Okay, so you've got bromine, which is orthopara directing, and nitro, which is meta directing. The order you add them must matter hugely.
That's the key. Start with benzene, nitrate it first, nitrobenzene. Then brominate that. The nitro group says, go meta, so you mostly get meta-bromonitrobenzene.
Okay.
But flip it. Start with benzene, brominate first para-bromonitrobenzene, then nitrate it. The bromo group directs orthopara, so you get a mixture of ortho and para-bromonitrobenzene. The sequence totally controls the outcome.
And what's even cooler, I think, is when you can actually change a directing group mid-synthesis, like reducing a meta-directing nitro group to an orthopara-directing amino group. That's like reprogramming the molecule's GPS.
Precisely. That gives you incredible flexibility. You can use the nitro group's meta-directing influence for some steps, then reduce it to an amine, NH2, and suddenly direct subsequent reactions to completely different spots on the ring. And combine that with diazonium chemistry, you can make things that are otherwise really hard to get, like 3-bromoiodobenzene. It's a powerful synthetic toolkit.
So far, we've mostly hit electrophilic substitution. What about the flip side? Nucleophilic aromatic substitution, SNAR. Does regioselectivity matter there too?
It does, absolutely.
Yeah.
For SNAR, you usually need an activating group, and nitro groups are great for that. But here's the thing. They only activate the ring for nucleophilic attack at the ortho and para positions.
Only ortho and para. Why not meta?
It comes down to stabilizing the intermediate. When the nucleophile attacks, you form a negatively charged intermediate, the Meisenheimer complex. That negative charge needs to be stabilized, and the nitro group can only effectively delocalize it through resonance if the attack happens ortho or para to it.
The resonance structures just don't work out if the attack is meta.
Exactly. No stabilization, much higher energy, reaction doesn't really happen. So again, electronics dictate the wear. It's another layer of regio control.
Okay, so we're building this picture of controlling reactions on rings. What about using the molecule's own structure to force regioselectivity, like in intramolecular reactions?
Yeah, that's a really clever strategy. You basically use a tether. You design the molecule so that the two reacting parts are physically held close together in just the right way. It forces a specific outcome that might be super difficult or impossible intermolecularly.
Like making tetralone using an intermolecular Friedel-Crafts acylation.
Classic example, you've got an acyl group on a chain attached to a benzene ring. When it cyclizes, it has to form that bond ortho to where the chain was attached. Guarantees that ortho relationship.
Very neat. Are there other good examples?
Oh yeah, halolectinization is a beautiful one, especially iolectinization. Imagine you have an alkene and somewhere nearby in the same molecule, a carboxylic acid group.
Okay.
You add a halogen, like iodine, I2. It reacts with the alkene to form that cyclic iodonium ion intermediate.
And then the nearby carboxylate, the COO anion, attacks it.
Yep. It snaps shut intramolecularly, usually forming a 5-membered lactone ring. And here's the regiochemistry kicker. The carboxylate almost always attacks the more substituted carbon of that original alkene within the iodonium ion.
So the ring closure itself is regioselective.
Highly regioselective, and then you can even pop open that lactone later and do more chemistry. It's multi-step control.
And you mentioned this sets up regioselectivity for later reactions too, like eliminations.
It certainly can. If you take that halolactone and do an elimination reaction, often it proceeds via an E1CB mechanism.
E1CB. That means you pull off a proton first, make an anion, then the leaving group leaves.
Right. And which proton gets pulled off is dictated by acidity, often influenced by that nearby ester group from the lactone. So the elimination is also regioselective, deciding exactly where the new double bond forms. One regioselective step setting up the next.
Wow. Okay, so we've covered aromatics and intramolecular tricks. What about just straightforward alkenes, adding things across the double bond? We know HBr addition usually follows Markovnikov's rule.
Right, the hydrogen goes to the carbon that already has more hydrogens because that forms the more stable carbocation intermediate.
Standard stuff. But what if you want the opposite? You want the OH group or the Bro atom on the less substituted carbon. Anti-Markovnikov.
Well, for making the anti-Markovnikov alcohol, hydroboration is the go-to method. Boron adds first to the less substituted end, and after oxidation, you get the alcohol there. It's the perfect counterpoint to acid-catalyzed hydration or oxymercuration.
Okay, so hydroboration gives anti-Markovnikov alcohols. But then things get really wild with radical reactions, don't they? They follow totally different rules.
Oh, completely different game.
Yeah.
Ionic reactions involve pairs of electrons moving, heterolytic cleavage. Radicals involve single electrons moving, homolytic cleavage. Think fishhook arrows.
And radicals, like carbocations, are electron deficient, so they're also stabilized by substitution. Tertiary radical more stable than primary.
Exactly. And this leads to one of the most striking examples of regiochemistry dictated by mechanism. Anti-Markovnikov HBr addition under radical conditions.
Right. If you add HBr to an alkene with, say, peroxides present to initiate radicals, you get the bromine on the less substituted carbon, the opposite of the ionic reaction.
It's mind-blowing when you first see it. And the reason is the bromine radical adds first in the radical mechanism, and it adds to the alkene in a way that generates the more stable carbon radical intermediate.
So if adding BRIO-R to the less substituted carbon forms a more stable secondary or tertiary radical, that's the path it takes.
Precisely. The bromine ends up on the carbon that started with more hydrogens, the anti-Markovnikov product. It's just a beautiful illustration of how fundamentally the mechanism controls the wear.
It really forces you to think about how the electrons or radicals are moving. Okay, what about allylic bromination? Using NBS, how does that work regioselectively?
NBS, and bromosuccinimide, is a clever reagent. Its job is to maintain a very, very low concentration of molecular bromine, Br2.
Why low concentration?
Because if you have a lot of Br2, it'll just add across the double bond via the ionic mechanism, bromonium ion, etc. But at low Br2 concentration, the radical pathway is favored. A bromine radical preferentially abstracts an allylic hydrogen.
Because the resulting allylic radical is resonance stabilizing?
Exactly. Super stable. That allylic radical then reacts with the tiny amount of Br2 present to form the allylic bromide product, regenerating a bromine radical to continue the chain. So NBS lets you selectively brominate the allylic position next to the double bond instead of adding to the double bond itself.
So even these highly reactive radicals can be steered precisely. Amazing.
Yeah. And that leads us nicely into nucleophilic attack on allylic systems, which is another area full of regioselectivity puzzles. Allylic compounds like allyl bromide,
where you have a leaving group on a carbon next to a double bond.
Right. They're quite reactive because of that conjugation. And nucleophiles have a choice. They can do a standard SN2 attack right on the carbon with the leaving group.
Or they can do an SN2 prime attack, hitting the other end of the double bond, causing the double bond to shift and the leaving group to get kicked out.
Exactly. It's a rearrangement pathway. What's happening electronically is that the LUMO, the lowest unoccupied molecular orbital, where the nucleophile attacks in these allylic systems, isn't just on the carbon with the leaving group, it actually extends over the double bond too. So attack can happen at either end.
So the challenge is controlling which one wins, SN2 or SN2.
Pretty much. Generally, sterics play a big role. The nucleophile tends to attack the less hindered end of the allylic system.
Okay, so for something like prenyl bromide, which is a primary carbon with the bromine and a tertiary carbon at the other end of the double bond,
the normal SN2 attack at the less hindered primary carbon is usually favored over the SN2 attack at the more hindered tertiary carbon.
Makes sense. But what if you really need regiospecificity, especially with allylic alcohols? They can isomerize easily, right?
They can, especially in acid. It makes control tricky. For primary allylic alcohols, sometimes using methane sulfonyl chloride, mansol chloride, and lithium chloride works okay because via SN2 keeps the alkene geometry. but it's often messy for secondary allylic alcohols.
So is there a better way for secondary ones?
Yes, Mitsunobu chemistry comes to the rescue here. Using specific Mitsunobu conditions, like with hexachloroacetone and triphenylphosphine, you can convert secondary allylic alcohols to chlorides with fantastic SN2 regioselectivity.
So direct replacement, no SN2.
Almost exclusively SN2, and it even retains the alkene geometry. It's remarkably clean, even if an SN2 product might look more stable. It's a really specific high-yield tool for that transformation.
Very powerful. What about making CC bonds if you want a carbon nucleophile to do an SN2 reaction?
For that, organometallic reagents are often the key, specifically copper reagents like Gilman reagents, R2-Celi, especially when you add a Lewis acid like BF3.
Gilman reagents, copper.
Oh, they are really good at promoting the SN2 pathway for carbon nucleophiles attacking allylic systems. Even with prenyl chloride, where you might expect SN2, these copper reagents can push the reaction towards the SN2 product, forming the new CC bond at the more hindered tertiary center. It's a vital tool for building carbon frameworks. Okay, incredible control there. We're covering a lot. Let's hit maybe two more key areas, conjugated dienes and those alpha-beta unsaturated carbonyls.
Right. Conjugated dienes, two double bonds separated by a single bond. They're more reactive than isolated double bonds.
And when an electrophile adds, you can get 12-orcyl-2 addition or 1-vol-4 addition. Exactly. The initial attack forms an allylic cation, which is resonance stabilized. The nucleophile can then attack at either end of that allylic system, giving either the WUS2 adduct or the 1-rel-4 adduct.
And this sounds like another kinetic versus thermodynamic situation.
Classic case. Low temperature usually favors the kinetic product, often the 12-2 adduct, which forms faster. But higher temperatures, or conditions where the addition might be reversible,
allow it to equilibrate to the more stable thermodynamic product, usually the 1,4 adduct, because it often results in a more substituted, more stable double bond.
Precisely. Think about bromine beta-tandine, depending on the conditions, temperature, solvent. You can favor one over the other.
Okay, and the final big category. Alpha, beta unsaturated carbonyls. Henols. We know nucleophiles can attack either directly at the carbonyl carbon, 1,4,2 addition, or at the beta carbon conjugate, or 1,4,4 addition. How is that controlled?
The balance of factors again. Product stability often favors conjugate 1,4 addition because you keep that strong carbon-oxygen double bond. But the carbonyl carbon itself is usually more electrophilic.
So the nucleophile type must matter a lot.
Huge difference. Hard, highly charged, very reactive nucleophiles, think Grignard reagents or organolithiums, tend to slam into the most electrophilic site, the carbonyl carbon, giving 1,4,2 addition.
Okay, hard goes 1,4,2.
Well, softer, less charged, more polarizable nucleophiles like amines, thiols, or those Gilman copper regions, again prefer the conjugate 1,4 addition pathway.
Soft goes 1,1,4. And the substrate matters too.
Yep. More reactive carbonyls like aldehydes or acid chlorides are more prone to direct 1-vol-2 attack. Less reactive ones like ketones or esters are more likely to undergo conjugate 1-vol-4 addition. And, as always, reversibility can play a role. If the 12-2 addition is reversible, it might equilibrate to the more stable 1-vol-4 product over time.
Phew, that's a ton of ways chemists steer reactions. Can we see it all come together in like a mini synthesis example?
Sure. Let's look at making a thiophenosaccharin analog. It's related to artificial sweeteners. One of the first steps involves reacting an unsaturated ester with a thiol.
A thiol. Sulfur nucleophile, that's soft, right?
Very soft. So where does it attack the unsaturated ester?
It should go for conjugate addition, attacks the beta carbon, the one before addition.
Exactly. It regioselectively adds to the beta carbon, avoiding the ester carbonyls.
Yeah.
That's step one, controlled by nucleophile softness.
Okay, what next?
Well, later on, there's a trickier step involving a diester reacting with a base. This forms an enolate, which then needs to attack another ester group intramolecularly to form a ring.
Ooh, that sounds like it could go multiple ways. Which ester forms the enolate? Which ester gets attacked? Lots of possibilities.
It absolutely can be messy. And in the actual published synthesis, getting the desired regioselectivity for that cyclization required careful control of the reaction conditions. Even then, the yield wasn't fantastic, maybe only moderate.
So sometimes it's not perfect, even with all this knowledge.
That's the reality of bench chemistry. Sometimes you push the regioselectivity as far as you can, accept a moderate yield of the desired product, and then rely on purification, maybe crystallization, like in this case, to isolate what you need. It's a blend of applying principles and practical problem solving.
That's a great dose of reality. It's not always clean textbook reactions.
Definitely not. But understanding these principles gives you the best chance of success.
Wow. What a journey through regioselectivity. We've gone from, guiding electrophiles on benzene rings with directing groups and blocking
To
groups,
using tethers in intramolecular reactions to force an outcome.
seeing how alkenes behave totally differently under ionic versus radical conditions,
Untangling SN2 versus SN2 for nucleophilic attack on allylic systems using things like Mitsunobu.
and then navigating the choices in conjugated dinenes and carbonyls, 12-mil-2 versus 1,4,4 addition.
It really boils down to understanding those key factors:
Mhm.
sterics, electronics, how stable the intermediates are, whether a reaction is reversible, the nature of the reagent. Get a handle on those and you can start to predict and control where bonds form.
It allows for those incredibly precise functional group transformations we see in complex synthesis.
Absolutely.
So next time you hear about a new medication or maybe a new polymer material, just think about the chemists behind it. They're like molecular architects, meticulously guiding reactions one bond at a time.
Making sure things happen, not just if they can, but exactly where they need to.
Yeah, it's this intricate dance, all governed by regioselectivity, that lets us build the molecular world around us. It's really fundamental.
Couldn't have said it better. It's molecular engineering at its finest.
Well, thank you for joining us on this deep dive into the where of chemical reactions. We hope you picked up some useful insights into the amazing precision of organic chemistry.